Must angular momentum belong to matter? In physics, angular momentum is generally understood through contributions such as spin angular momentum and orbital angular momentum. Existing decompositions seek to account for the total angular momentum budget through these matter field contributions. This discussion begins by asking whether an ontological assumption in existing decompositions is actually necessary. Must every physically meaningful contribution to angular momentum be realized exclusively within matter fields? The question is motivated by the observation that the decomposition of angular momentum can remain conceptually open even when conservation of the total quantity is not. The proton spin problem serves as one example. Its significance here is not that it demonstrates a geometric contribution to angular momentum, nor that the present discussion attempts to address proton structure itself. Rather, it illustrates that questions concerning how angular momentum should be partitioned and interpreted can remain open despite agreement that the total quantity is conserved. If that ontological assumption is relaxed, another possibility becomes available. Physically meaningful contributions to angular momentum need not be realized exclusively within matter fields. One possible way of exploring that possibility is through a geometric ontology. Within the present proposal, a Riemann-Cartan-type spatial manifold provides the ontological starting point from which the physical description is developed. In that sense, the framework does not separate geometry from space as distinct ontological categories. Rather, the spatial manifold is already geometric, and together they provide the ontological starting point for investigating whether the total angular momentum budget may include a geometric contribution alongside existing matter field contributions. The immediate task then becomes identifying a geometric mechanism through which such a contribution, if it exists, might be realized. Within the present conceptual direction, the ontological starting point is a Riemann-Cartan-type spatial manifold equipped with a Poincaré gauge connection, interpreted within a non-minimal Einstein-Cartan extension, in which torsion remains dynamical, providing a second geometric degree of freedom alongside curvature. Within this ontology, the geometrically structured spatial manifold acts as the carrier structure, while the Poincaré gauge connection provides the relational and transport structure through which physical relations are realized. Curvature and torsion constitute the available geometric degrees of freedom, while the contortion sector describes how torsion modifies the connection without introducing an additional independent degree of freedom. Dynamical torsion therefore becomes the candidate mechanism through which a geometric contribution to the total angular momentum budget might be realized. Importantly, the present framework does not propose a geometric contribution within Euclidean structure, nor does it attempt to bridge directly between proton-scale physics and cosmological structure. The immediate framework operates at cosmological scales. The proton spin problem motivates the question rather than the scale. Instead, the proposed contribution is sought within the effective geometric description of large-scale cosmic structure. Within a Buchert average timescape cosmology, torsion may contribute to the effective angular momentum budget through its influence on domain-scale geometry. In that context, any geometric contribution would be expected to manifest not through proton structure, but through vorticity, rotation, and their contribution to kinematic back-reaction across cosmological domains. The framework, therefore, does not replace existing matter field contributions such as spin or orbital angular momentum. Instead, it asks whether those contributions are exhaustive. Existing decompositions of angular momentum assume that physically meaningful contributions are realized within matter fields. The framework questions whether that ontological assumption is necessary. If it is relaxed, the hypothesis follows that the geometrically structured spatial manifold, through dynamical torsion as a second geometric degree of freedom, may legitimately contribute to the total angular momentum budget. Within the present cosmological implementation, that contribution is explored through its manifestation in the effective angular momentum budget, arising from a Buchert average timescape description. More broadly, the proposal develops a geometric ontology in which persistence is realized through geometry rather than through time. Time is not treated as the carrier of change, but as its index. The Riemann-Cartan-type spatial manifold, together with its Poincaré gauge connection, provides the conceptual direction through which persistence, transport, and physical relations may be understood geometrically. How far that geometric ontology ultimately extends remains a question for the continued development of the framework. Its immediate objective is more specific: to investigate whether the geometrically structured spatial manifold, through its second geometric degree of freedom, may contribute to angular momentum accounting and to explore the physical consequences that follow if that possibility proves meaningful.